quantum decoherence, why the quantum world appears classical. We discovered that space is filled with quantum fields. We learned that everything, light, matter, you, waves through those fields. But here's the puzzle. If everything is quantum, if atoms and electrons exist in superposition, why don't you? Why does the world appear solid, definite, classical, when fundamentally it's not? Welcome back to Sleep Entangled, where quantum mysteries and contemplative wonder merge into nocturnal voyages. We've journeyed through quantum fields and wave-particle duality. Now we ask the deepest question: why does quantum strangeness vanish at large scales? What builds the bridge between the quantum realm and the classical world you experience? If you find depth in these explorations, remember to subscribe and let curiosity guide your nights. Now, settle in, breathe slowly, and let's discover why reality hides its quantum nature. Chapter 1: The Quantum Mystery. Why don't we see superposition? The paradox of scale. We've established something profound. Everything is quantum. Electrons exist in superposition, simultaneously occupying multiple states until measured. Photons pass through two slits at once, interfering with themselves. Atoms diffract like waves. Even large molecules, buckyballs containing 60 carbon atoms, exhibit quantum interference. The mathematics is clear. Schrodinger's equation applies to all systems, regardless of size. There's no term in the equation that says quantum mechanics stops working when objects get big. The wave function should describe everything: electrons, atoms, molecules, bacteria, cats, humans, planets, galaxies. And yet, you don't observe yourself in superposition. You've never been in two places at once. You've never seen a cat that's both alive and dead. Baseballs don't diffract. Buildings don't interfere with themselves. The quantum world, strange, probabilistic, wave-like, somehow gives rise to the classical world, definite, deterministic, particle-like. But how? What mechanism transforms quantum blur into classical clarity? For decades, this was quantum mechanics' deepest mystery. The theory worked perfectly at small scales but seemed disconnected from everyday experience. Physicists could calculate probabilities for electron behavior with stunning precision, yet couldn't explain why a chair stays in one place. The answer is decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment, and it's one of the most important discoveries in physics, quietly revolutionizing our understanding of reality over the past 40 years. The measurement problem. To understand decoherence, we must first understand the measurement problem, the central puzzle of quantum mechanics. Schrödinger's equation describes how quantum systems evolve over time. It's deterministic, continuous, and linear. A system in superposition remains in superposition, evolving smoothly according to the equation. But when you measure the system, something dramatic happens. The superposition collapses. The wave function, spread across multiple possibilities, instantly becomes localized in one definite state. The electron that was everywhere becomes here. The photon that went through both slits chooses one path. This collapse is discontinuous, instantaneous, and probabilistic. It seems completely different from the smooth evolution described by Schrödinger's equation. The measurement problem asks, what causes collapse? Is it a real physical process or just an update of our knowledge? Does measurement require consciousness, or is it a purely physical interaction? And why does measurement cause collapse while other interactions don't? For much of the 20th century, physicists had no good answer. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, simply declared that measurement is fundamental, a special kind of interaction that causes collapse. Don't ask what collapse really is or why it happens, just calculate probabilities and move on. This was pragmatic but unsatisfying. It divided the world into quantum systems, governed by Schrodinger's equation, and classical measuring devices, which somehow cause collapse. But measuring devices are made of atoms, which are quantum. So where's the boundary? When does quantum become classical? Schrodinger's cat. In 1935, Erwin Schrödinger, one of the founders of quantum mechanics, proposed a thought experiment to illustrate the absurdity of applying quantum rules to large systems. Imagine a cat in a sealed box with a diabolical device. Inside the box is a radioactive atom with a 50% chance of decaying in 1 hour. If it decays, it triggers a mechanism that releases poison, killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, before you open the box, the atom exists in a superposition, 50% decayed, 50% undecayed. This superposition couples to the poison mechanism, which enters superposition, 50% triggered, 50% not triggered. This couples to the cat, which enters superposition, 50% dead, 50% alive. So before you open the box, the cat is in a superposition of alive and dead, neither fully one nor the other, but both simultaneously, described by a single quantum wave function. But this seems ridiculous. Cats aren't observed in superposition. When you open the box, you find the cat either alive or dead, not both. Common sense says the cat was definitely alive or definitely dead before you looked. The superposition can't apply to something as large and complex as a cat. Schrödinger intended this as a criticism of quantum mechanics, a demonstration that the theory's implications are absurd when extended to macroscopic objects. But he was pointing to a genuine puzzle. Where does quantum mechanics stop applying? And if it doesn't stop, why don't we observe macroscopic superpositions? The answer, it turns out, is not that quantum mechanics stops working. It's that the environment, the air, the photons, the thermal radiation surrounding the cat, constantly interact with the cat, destroying the superposition almost instantaneously. The cat is always quantum, but the cat's quantum state is so thoroughly entangled with its environment that the superposition becomes unobservable. The cat appears classical, not because it is classical, but because decoherence hides its quantum nature. For decades after Schrödinger proposed his cat, physicists struggled to understand the quantum to classical transition. They knew quantum mechanics applied at small scales, and classical mechanics at large scales. But the mechanism linking them remained mysterious. In the 1970s and 80s, a new understanding emerged, pioneered by physicists like Hans-Dieter Zeh, Wojciech Zurek, Erich Hughes, and others. They developed the theory of decoherence, the idea that quantum systems lose coherence not through some mysterious collapse process, but through ordinary quantum interactions with their environment. Decoherence doesn't solve the measurement problem entirely. It doesn't tell us whether wave functions truly collapse or whether the many worlds interpretation is correct. But it explains why superpositions become unobservable at large scales, and that's a huge step forward. It explains Schrödinger's cat. It explains why baseballs don't diffract. It explains why you appear to have a definite position even though, fundamentally, you're a quantum wave. And it does this without invoking consciousness, without dividing the world into quantum and classical, and without adding anything to the standard quantum formalism. Decoherence emerges naturally when you account for the fact that real systems are never truly isolated. They're always interacting with their surroundings. Here's what makes decoherence remarkable. It's incredibly fast for macroscopic objects. For a dust grain floating in air, decoherence occurs in about 10 to the minus 23 seconds, far faster than any timescale you can measure. The grain is constantly being bombarded by air molecules, each collision entangling the grain's quantum state with the environment. For a larger object like a bacterium, decoherence is even faster. For a human being, it's essentially instantaneous, trillions upon trillions of environmental interactions per second, each one entangling your quantum state with the world around you. This is why you never observe yourself in superposition. Not because superposition doesn't exist for large objects, but because it decoheres so quickly that it's gone before you could possibly observe it. The quantum world doesn't disappear at large scales. It's just hidden, obscured by the overwhelming rapidity of decoherence. As you rest tonight, consider this. Every atom in your body exists in a quantum superposition, a blur of possibilities. But every instant photons bounce off you, air molecules collide with you, thermal radiation bathes you. Each interaction entangles you with your environment, collapsing tiny pieces of your quantum state, over and over, billions of times per second. You are quantum, you wave, you exist in superposition. But decoherence sculpts that quantum chaos into the definite, solid form you perceive as yourself. The world is quantum. The classical appearance is a veil, woven by decoherence, hiding the strange truth beneath. Let us now explore how this veil is woven, the mechanism of decoherence itself. Chapter 2. The environment as witness. The ideal versus the real. In textbooks, quantum systems are often treated as isolated, perfectly sealed off from the rest of the universe, evolving according to Schrodinger's equation without any external interference. This isolation is necessary to see quantum effects. A photon in superposition of two paths will exhibit interference only if nothing watches which path it takes. An electron in a superposition of two positions will show wave-like behavior only if its position isn't measured by the environment, but perfect isolation is a fiction. In reality, every system interacts with its surroundings. Photons scatter off objects, air molecules collide with surfaces, thermal radiation bathes everything above absolute zero. Even the vacuum isn't empty. Quantum fluctuations produce virtual particles that briefly interact with matter. These environmental interactions are unavoidable, and each one carries information about the system's quantum state. When a photon scatters off an electron, the photon's state becomes correlated with the electron's position. When an air molecule bounces off a dust grain, the molecule's trajectory depends on where the grain is. The environment, in effect, is constantly measuring the system, not with scientific instruments, but through myriads of tiny, uncontrolled interactions, and these measurements destroy quantum coherence. Entanglement, the key mechanism. Here's the crucial insight. Decoherence is fundamentally about entanglement. Imagine an electron in a superposition of being at position A or position B. Pieces equals A plus B. This is a coherent superposition. If you set up an interference experiment, the two components A and B can interfere, producing observable quantum effects. Now suppose a photon scatters off the electron. If the electron is at A, the photon scatters one way. If the electron is at B, the photon scatters a different way. The combined state becomes pulse equals I see photon scattered from A plus B, photon scattered from B. The electron and photon are now entangled. The electron's state is no longer a simple superposition. It's correlated with the photon's state. If you try to observe interference in the electron's position, you'll find that the interference pattern has vanished. The electron behaves as if it's definitely at A or definitely at B, not both. But mathematically, the superposition is still there. It's just spread across the electron-photon system. The electron alone no longer shows quantum behavior because its state is entangled with the photon. Now imagine not one photon but billions, thermal photons, scattered light, cosmic rays, all interacting with the electron. Each interaction entangles the electron further with the environment. The superposition doesn't disappear, but it becomes so thoroughly distributed across countless environmental degrees of freedom that it's completely unobservable. This is decoherence. The quantum system is still described by a wave function, still in superposition, but the superposition is hidden in the correlations with the environment. Why information matters? You might wonder. Why does entanglement with the environment destroy coherence? Why can't we just ignore the environment and focus on the system? The answer lies in information. When the environment becomes entangled with the system, information about the system's quantum state leaks into the environment. That information is now stored in the positions and momenta of countless photons, air molecules and other environmental particles flying away in all directions. To recover the system's quantum coherence, to observe interference, you would need to gather all that information back, to track every environmental particle and reverse the entanglement. But this is practically impossible. The information is irreversibly dispersed, so while the system's quantum state hasn't truly collapsed, it's still described by a wave function. The system behaves as if it has collapsed. For all practical purposes, the superposition is gone. This is sometimes called effective collapse or apparent collapse. The wave function remains, but interference effects are suppressed to such a degree that the system appears classical. The rate of decoherence. How fast does decoherence occur? It depends on two factors: the size of the system and the strength of its coupling to the environment. Large systems couple more strongly because they have more surface area, more atoms, more ways to interact with the environment. A dust grain has vastly more decoherence channels than a single electron. Warm systems decohere faster than cold systems because thermal radiation increases with temperature. At room temperature, objects emit and absorb countless infrared photons, each one entangling the object's state with the electromagnetic field. Dense environments, like air, cause faster decoherence than sparse environments, like vacuum, because molecular collisions are frequent. For a single electron in ultra-high vacuum at ultra-low temperature, decoherence can be very slow, seconds, even minutes. This allows delicate quantum experiments like atom interferometry and quantum computing. But for a macroscopic object at room temperature in air, decoherence is extraordinarily fast. A dust grain decoheres in 10 to the minus 23 seconds. A bacterium decoheres even faster. A cat, a human, a chair. Decoherence is essentially instantaneous, far faster than any timescale we can perceive. This is why quantum mechanics seems irrelevant to everyday life. Not because large objects aren't quantum, but because their quantum nature is instantaneously obscured by decoherence. The irreversibility of decoherence. In principle, decoherence is reversible. If you could track every environmental particle and perform the inverse of every interaction, you could disentangle the system from the environment and restore quantum coherence. This is called quantum error correction, and it's the foundation of quantum computing. Quantum computers fight decoherence by continuously monitoring and correcting errors before information leaks irreversibly into the environment. But for macroscopic objects, this is hopeless. There are too many environmental degrees of freedom. 10 to the 23rd photons, 10 to the 26th air molecules, countless quantum field fluctuations. Tracking and reversing all those interactions is beyond any conceivable technology. So while decoherence is theoretically reversible, it's practically irreversible. Once information leaks into the environment, it's gone. The quantum coherence is destroyed, and the system appears classical. This irreversibility is why decoherence provides an arrow of time, a direction to the flow of time. Quantum states decohere into classical states, not the reverse. This is analogous to the thermodynamic arrow of time, where entropy increases and order degrades. Indeed, decoherence and entropy are closely related. Both involve information becoming dispersed across many degrees of freedom. Both are practically irreversible. Both explain why the past is different from the future. Decoherence doesn't require consciousness. One crucial point: decoherence happens through ordinary physical interactions. It doesn't require consciousness, observers, or measurements in any special sense. The environment doesn't know it's measuring the system. Photons don't observe in any conscious way. Decoherence is just quantum mechanics applied to open systems, systems that interact with their surroundings. This resolves one of the strangest aspects of the Copenhagen interpretation, which seemed to give consciousness a special role in quantum mechanics. If only conscious observation causes collapse, then the universe before life would have been in a perpetual quantum superposition, a bizarre implication. Decoherence shows that collapse, or at least effective collapse, happens automatically, continuously, through environmental interaction. Consciousness may experience the results of decoherence, but it doesn't cause decoherence. The universe was collapsing wave functions long before minds evolved to observe it. Photons were decohering atoms, atoms were decohering molecules, thermal radiation was decohering planets, all without any consciousness involved. The role of the observer. So, if consciousness doesn't cause decoherence, what role do observers play? Observers are special only in that they're complex systems capable of recording information. When you measure an electron's position, you're creating a correlation between the electron's state and your measuring device's state, which in turn correlates with your brain state, which correlates with your conscious experience. This chain of correlations is just entanglement, the same process that underlies decoherence. There's nothing special about the final step, consciousness, compared to the earlier steps, device, photons, environment. But from the observer's perspective, the correlation matters because it determines what you experience. You become entangled with one branch of the wave function, experiencing it as real, while other branches persist in the larger universal wave function, but remain inaccessible to you. This is the many worlds picture, where observers don't collapse wave functions, but rather become entangled with particular branches, experiencing those branches as unique realities. Alternatively, in objective collapse theories, decoherence may trigger actual collapse through some as yet unknown physical mechanism, like gravity at the Planck scale. Observers then experience the post-collapse reality. Either way, decoherence explains the appearance of classical reality without requiring observers to play a fundamental role in quantum mechanics. So, as you settle deeper into stillness, imagine the environment as a witness, constantly, silently, watching everything, not with eyes or consciousness, but with photons and molecules and fields, each one carrying away a tiny piece of information about the quantum world. Every atom in your body is being watched by this environment. Every electron, every photon, every quantum state is entangled with countless degrees of freedom, spreading information across space, decohering possibility into actuality. You are not isolated. You're immersed in a bath of interactions, perpetually decohering, perpetually collapsing from quantum blur into classical clarity. And this is not a failure of quantum mechanics. This is quantum mechanics working exactly as it should. Now, let us turn to the mathematics, how decoherence unfolds, and what it means for the structure of reality. Chapter 3. Entanglement spreads like wildfire. The spreading of correlations. We've established that decoherence is fundamentally about entanglement between a system and its environment. But how does this entanglement spread? And why does it happen so quickly for large systems? To understand this, we need to think about the structure of entanglement itself. Imagine a single photon scattering off an electron. Before the interaction, the electron is in a superposition of positions, and the photon has a definite state, say, travelling in a specific direction. After the interaction, the electron and photon are entangled. The photon's state now depends on where the electron was when they interacted. This single interaction slightly degrades the electron's coherence, but it's a small effect, 1 degree of freedom, the photon, entangled with one electron. Now imagine a second photon scattering, then a third, then a fourth. Each interaction adds another degree of freedom to the entanglement. The electron's state becomes correlated with photon 1, photon 2, photon 3, and so on. By the time billions of photons have scattered, the electron's state is entangled with an enormous number of environmental degrees of freedom. The quantum coherence is completely hidden in this vast web of correlations, and this happens incredibly fast. Thermal photons scatter at rates determined by temperature and surface area. At room temperature, a single dust grain interacts with roughly 10 to the power of 10 photons per second. Each photon flies away, carrying information, spreading the entanglement further. This is why decoherence is so rapid for macroscopic objects. It's not that one big interaction destroys coherence, it's that countless tiny interactions spread entanglement exponentially through the environment. Decoherence is branching. Here's another way to picture it. Imagine the electron starts in a superposition, psi equals A plus B. After one photon scatters, psi equals A, photon from A plus B, photon from B. The state has branched into 2 correlated components. The photon carries information. Electron was at A, or electron was at B. After a second photon scatters, Laplans equals A, photon 1 from A, photon 2 from A, plus photon 1 from B, photon 2 from B. Now 2 photons carry redundant information. The branching has spread. After billions of photons, B equals A, billions of photons encoding A, plus B, billions of photons encoding B. The 2 branches are now macroscopically distinct. The photons in one branch have all scattered in directions consistent with the electron at A. The photons in the other branch have scattered consistently with the electron at B. These branches no longer interfere. The terms in the superposition are orthogonal. They correspond to completely different environmental states. Interference requires overlap, and there's no overlap between billions of photons arranged one way versus billions arranged another way. So the electron superposition is still mathematically present, but it's unobservable. The electron behaves as if it's at A or B, not both. This is decoherence, and it's also the basis of the many worlds interpretation. Each branch corresponds to a world, and observers become entangled with one branch, experiencing it as the unique reality. Exponential spreading, the key insight. Decoherence spreads exponentially. Each environmental particle that interacts can go on to interact with other particles, spreading the information further. A photon that scatters off an electron might then hit a wall, transferring its energy to atoms in the wall, which vibrate and emit more photons, which travel elsewhere and interact with other matter, and so on. Within microseconds, information about the electron's position has spread throughout the room, encoded in countless particles and fields irreversibly dispersed. This exponential spreading is why reversing decoherence is so difficult. You'd need to track not just the first photon, but every particle it subsequently interacted with, and every particle those particles interacted with, and so on. A tree of interactions expanding exponentially. For a single photon in a carefully controlled laboratory, this might be achievable. For a macroscopic object in an uncontrolled environment, it's hopeless. The quantum to classical transition decoherence provides a quantitative answer to the question, when does quantum become classical? The transition is not sharp. It's gradual, depending on the system's size and its coupling to the environment. For an electron in isolation, decoherence might take seconds or longer. The electron remains quantum. For a large molecule like a buckyball, decoherence happens in milliseconds in air, but can be slowed to seconds in ultra-high vacuum. The molecule is on the border between quantum and classical. For a dust grain, decoherence is in the microsecond range, still measurable but difficult to avoid. For anything larger, decoherence is instantaneous on any practical timescale. The object is effectively classical. So the quantum to classical transition is not about a fundamental change in physics. It's about the timescale of decoherence relative to the timescale of observation. If decoherence is faster than your observation, the system appears classical. If decoherence is slower, quantum effects are observable. This is why building quantum computers is so hard. You need to perform quantum computations faster than decoherence destroys the quantum state. This requires extreme isolation, ultra-low temperatures, ultra-high vacuum, shielding from electromagnetic radiation. And even then, decoherence limits computation time to microseconds or milliseconds. Why size matters. Why do large objects decohere faster than small ones? The answer is surface area and the number of internal degrees of freedom. A large object has more surface area, so more photons scatter off it per unit time. It also has more atoms, each one a potential site for interaction with the environment. Moreover, large objects have internal structure, vibrational modes, thermal motion, internal electromagnetic fields. These internal degrees of freedom can also entangle with the environment, accelerating decoherence. A single electron is simple. It has position, momentum, spin, and not much else. A dust grain has 10 to the 15th atoms, each vibrating, each interacting with neighbours, each coupling to electromagnetic fields. The number of ways the grain can entangle with the environment is vastly larger. This is why macroscopic superpositions are so rare. The larger the system, the faster it decoheres, and the harder it is to observe quantum behaviour. An important subtlety. Decoherence doesn't destroy all superpositions equally. It preferentially destroys superpositions in certain bases, particularly superpositions of different positions. This is because environmental interactions, photon scattering, molecular collisions, primarily depend on position. A photon scattering off an object carries information about where the object is, not about how fast it's moving or what its energy is. So positions superpositions decohere rapidly, while momentum superpositions decohere more slowly. This is why macroscopic objects appear to have definite positions, but can still have uncertain velocities, like molecules in a gas, which have definite locations but random velocities. The basis in which decoherence is fastest is called the pointer basis. the set of states that are most robust against environmental interaction. For position, these are localized states, states where the object is here rather than spread out. This is why the classical world appears to have definite positions. Decoherence selects position as the preferred observable, suppressing superpositions of different locations while leaving other properties less constrained. For quantum systems, we define a coherence time, the timescale over which quantum coherence survives before decoherence destroys it. For an electron in vacuum at low temperature, the coherence time can be very long, seconds, even hours in the best experiments. For a superconducting qubit, used in quantum computers, cooled to millikelvin temperatures and shielded from radiation, the coherence time is on the order of microseconds to milliseconds, long enough to perform calculations but short enough to be a major engineering challenge. For a molecule at room temperature in air, the coherence time is picoseconds or less. For a macroscopic object, the coherence time is so short it's essentially zero, far below any measurable timescale. This coherence time determines what quantum phenomena are observable. If an experiment takes longer than the coherence time, decoherence will destroy the quantum state before the experiment finishes, and you'll see classical behavior instead. So as you rest, picture entanglement spreading through space like ripples on a pond. A single interaction, a photon scattering, an air molecule colliding, creates a ripple, a correlation between system and environment, but that ripple doesn't stop. It propagates, interacts with other systems, creates more ripples, branching exponentially, filling space with a vast web of correlations. Within moments, the entire room is entangled with your quantum state. The walls, the air, the photons bouncing between surfaces, all carry information about you, all correlated with your wave function. You are not isolated. You are embedded in this web, perpetually entangling, perpetually decohering. And this is not an enemy of quantum mechanics. This is quantum mechanics revealing its full richness, a universe not of isolated particles, but of interconnected, entangled systems woven together by interaction. Now, let us explore what this means for the nature of reality itself. Chapter 4, Besusterstath, Pointer States, Nature's Preferred Reality. Robust states. We've seen that decoherence destroys quantum coherence by spreading entanglement into the environment, but not all quantum states decohere at the same rate. Some states are more robust, more resistant to environmental interaction than others. These robust states are called pointer states, named after the idea that they're the states the environment points to, the states that remain stable even as the environment interacts with the system. Pointer states define what we perceive as classical properties. They're the states that survive decoherence, the states that appear definite and real, while other superpositions are rapidly destroyed. Understanding pointer states is key to understanding why the world looks the way it does, why objects have definite positions, why certain properties seem more real than others. The pointer basis. Imagine a quantum system interacting with its environment. Some states of the system cause minimal disturbance to the environment. The environment's state barely changes. Other states cause large disturbances. The environment's state changes significantly. The states that cause minimal disturbance are the pointer states. They're eigenstates of the interaction Hamiltonian, the operator describing how the system and environment interact. For position-based interactions, like photon scattering or molecular collisions, the pointer states are localized position states. An object here scatters photons one way, an object there scatters photons a different way. so here and there are stable, distinguishable pointer states. Superpositions of here and there, however, are not pointer states. Such superpositions lead to entanglement with the environment, and decoherence rapidly destroys them. This is why macroscopic objects appear to have definite positions. Position is the pointer basis for most environmental interactions. Superpositions of position decohere almost instantaneously, leaving only localized states observable, energy eigenstates. For some systems, energy eigenstates, states with definite energy, are pointer states. Consider an atom interacting with thermal radiation. If the atom is in an energy eigenstate, like its ground state or an excited state, it emits and absorbs photons in a predictable way. The thermal environment doesn't significantly disturb the atom's state, but if the atom is in a superposition of different energy levels, the environment can decohere this superposition, forcing the atom into a definite energy state. This is why atoms in isolation seem to have definite energy levels. Superpositions of energy decohere, though often more slowly than superpositions of position. For quantum computers, the challenge is to design qubits whose computational basis states are pointer states, states that don't decohere rapidly. This is why superconducting qubits are cooled to millikelvin temperatures and shielded from electromagnetic radiation. The goal is to make the qubit's superposition states robust against decoherence. Why position dominates. In the macroscopic world, position dominates. Chairs have definite locations. People are here or there, not in superpositions of different places. This is because position-based interactions, photon scattering, molecular collisions, are by far the strongest coupling between macroscopic objects and their environment. A chair at position A reflects light differently than a chair at position B. The light carries information about the chair's location, rapidly decohering superpositions of A and B. But the chair's velocity, or its internal energy, doesn't couple as strongly to the environment. So while the chair has a definite position, pointer state, it might have slight uncertainty in velocity or thermal energy less strongly selected by decoherence. This is why classical mechanics focuses on position and momentum. Position is the pointer basis, and momentum is conjugate to position. Other properties, spin, energy, phase, become secondary because they decohere more slowly or don't directly couple to macroscopic observations. Decoherence selects reality. Here's a profound implication. The properties we perceive as real, position, shape, velocity, are not intrinsic to quantum mechanics. They're selected by decoherence. In a universe without environmental interaction, there would be no preferred basis. Superpositions of position, momentum, energy, and every other observable would be equally valid. The universe would be a vast, undifferentiated quantum blur. But in our universe, with its omnipresent thermal radiation, electromagnetic fields, and molecular motion, certain bases are preferred. Position decoheres fastest, so position becomes real. Energy is more stable, so energy levels become definite. Reality in this sense is not fundamental, it's emergent, a consequence of how quantum systems interact with their environments. This is a startling idea. It means that if the environment were different, if the dominant interactions were different, the structure of observable reality would be different. Perhaps position wouldn't be definite. Perhaps energy or momentum or some other property would dominate. We live in a universe structured by decoherence. The classical world we perceive is a selection, one possibility among many, chosen by the specific way our environment interacts with matter, the predictability sieve. Wojciech Zurek, one of the pioneers of decoherence theory, introduced the concept of the predictability sieve. The idea, pointer states are predictable. If a system is in a pointer state, its future evolution is relatively stable and predictable, even as it interacts with the environment. Non-pointer states, by contrast, are unstable. They rapidly become entangled with the environment, their evolution unpredictable due to the chaotic nature of environmental interactions. The environment, in effect, sieves through all possible quantum states, allowing only the predictable ones, pointer states, to persist, while washing out the unpredictable ones, superpositions. This is why classical mechanics works so well for macroscopic objects. The objects are in pointer states, so their behavior is predictable, deterministic, on average, and follows simple laws like Newton's equations. Quantum mechanics, by contrast, applies to non-pointer states, superpositions that haven't yet decohered. These states are unpredictable, probabilistic, and follow the more complex rules of quantum dynamics. Classicality, then, is predictability. The classical world is the set of states that remain stable and predictable despite environmental interaction. Superselection rules. In some cases, decoherence is so strong and so universal that certain superpositions are never observed, even in carefully controlled experiments. These are called superselection rules. For example, you never observe superpositions of different electric charge. A particle is either charged or neutral, never both. This is because electromagnetic interactions couple so strongly to charge that any superposition of charge states decoheres essentially instantaneously. Similarly, you never observe superpositions of macroscopically different masses. A star doesn't exist in a superposition of having one solar mass and two solar masses. The gravitational field couples so strongly to mass that such superpositions are immediately decohered by gravitational interactions with the rest of the universe. Superselection rules arise from decoherence. They're not fundamental prohibitions in quantum mechanics, they're practical impossibilities due to unavoidable environmental coupling. This suggests that many of the rules we observe in nature, constraints on what superpositions are possible, are not fundamental laws but emergent consequences of decoherence. Environmental Darwinism. Here's a poetic way to think about pointer states. They're the fittest quantum states, the ones that survive in the presence of environmental interaction. Superpositions are fragile. They require isolation, careful control, precise conditions. Expose them to the environment, and they quickly die, decohering into pointer states. Pointer states, by contrast, are robust. They withstand environmental battering, remaining stable and definite. In this sense, the classical world is the result of natural selection at the quantum level. The environment selects for stable, predictable, definite states. Everything else, all the delicate quantum superpositions, is washed away by decoherence, leaving only the pointer states observable. We live in a world shaped by this selection process. The properties we perceive, position, shape, motion, are the survivors, the fittest states, the ones that can persist in a universe filled with interaction. Imagine now the quantum states flickering through your body, electrons in superposition, atoms vibrating, molecules shifting. But most of these superpositions are fleeting, unstable, decohering within fractions of a second. Only the pointer states persist, the stable configurations, the definite positions, the predictable energies. These are what you perceive, what you experience as real. But beneath that stability, the full quantum richness remains, hidden, entangled, woven into the environment, waiting for the right conditions to reveal itself. Reality is a selection, and you are living in the states that survived. Now, let us turn to a fascinating extension of this idea: quantum Darwinism. the theory that explains why multiple observers see the same reality. If you're still with me in this late-night journey through the quantum classical boundary, you're part of something rare. Seekers willing to explore the mechanisms that shape reality itself. A quick subscribe helps others discover this contemplative voyage through decoherence and the emergence of the classical world. Now let's continue deeper into the quantum Darwinism, the reason we all see the same universe. Chapter 5. Quantum Darwinism. Why reality looks classical to everyone. The objectivity problem. We've seen that decoherence makes superpositions unobservable, causing quantum systems to appear classical. But this raises a new question. Why do different observers agree on what they observe? If I look at a chair and see it here, and you look at the same chair, you also see it here. We agree. The chair's position is objective, independent of who observes it. But in quantum mechanics, observation entangles the observer with the observed system. When I look at the chair, I become entangled with one branch of the chair's wave function. When you look, you become entangled with potentially a different branch. So why do we end up in the same branch? Why do we agree on the chair's position? This is the objectivity problem. Decoherence explains why individual observers see definite outcomes, but it doesn't immediately explain why different observers see the same outcomes. The answer is quantum Darwinism, a theory developed by Wojciech Zurek that explains how objective reality emerges from quantum mechanics through the proliferation of information into the environment. Redundant information. The key insight of quantum Darwinism: pointer states imprint multiple copies of their information into the environment. When a photon scatters off a chair, it carries information about the chair's position. The chair is here. But it's not just one photon. Countless photons scatter, each one carrying the same information. Chair here. This redundancy is crucial. If only one photon carried the information, different observers might intercept different photons and see different things. But because many photons carry the same information, any observer intercepting any subset of photons will see the same thing. The chair's position is encoded redundantly in the environment. This redundancy makes the information objective, accessible to multiple observers independently without disturbing the original. This is what we mean by objective reality. It's not that the chair has a position independent of observation. It's that the chair's position is encoded so redundantly in the environment that every observer who interacts with that environment sees the same position. Think of the environment as a communication channel between the system and observers. The system, the chair, broadcasts information about its pointer states, its position, into the environment: scattered photons, air molecules, thermal radiation. This broadcast creates many copies of the information spreading through space. Observers, you, me, measuring devices, tune into this broadcast by interacting with the environment. Because the broadcast is redundant, we all receive the same information. Non-pointer states, by contrast, do not proliferate information redundantly. Superpositions lead to entanglement, but not to multiple copies of the same information. Different environmental fragments carry different, incompatible information, so observers don't agree. This is why we can't see superpositions. Not only do they decohere rapidly, but the information they contain is not redundantly copied into the environment. It's hidden, inaccessible to observers. Darwinian selection of information. The name quantum Darwinism comes from an analogy with biological natural selection. In biology, organisms that are fit, well adapted to their environment, produce many offspring, spreading their genes widely. Unfit organisms produce few offspring and disappear. Similarly, in quantum mechanics, pointer states, well adapted to environmental interaction, produce many copies of their information, spreading through the environment. Non-pointer states produce few or no redundant copies and quickly vanish. The information that survives, that proliferates, that becomes accessible to multiple observers, is the information about pointer states. This is the information we call classical reality. So, the classical world is not just stable, decoherence, it's also objective, quantum Darwinism. The same information is available to everyone because pointer states proliferate their information abundantly. Spectrum broadcasting. Zurek uses the metaphor of spectrum broadcasting to describe this process. Imagine the environment as a spectrum, a collection of many channels, photons, air molecules, field modes. The system, like a star or a chair, broadcasts its pointer state information across this spectrum, encoding the same information in many channels. Observers tune into different channels. If you look at the star, you intercept some photons. If I look, I intercept different photons. But because the information is redundantly encoded across the spectrum, we both see the same thing. The star's position, its brightness, its colour. This redundancy is what makes the star objective. Its properties are not private, not hidden, not unique to one observer. They're public, accessible, shared. And this happens automatically, without any special role for consciousness or measurement. The environment naturally creates redundancy for pointer states, making them objective. How much redundancy? For a macroscopic object, the redundancy is enormous. A single dust grain scatters billions of photons per second. Each photon carries information about the grain's position, so there are billions of copies of the information "grain is here" flying through space. This extreme redundancy is why macroscopic objects seem so solidly real, so undeniably objective. The information is everywhere, encoded in countless environmental degrees of freedom, accessible to any observer who looks. For microscopic systems, redundancy is less. A single electron might scatter only a few photons. The information about the electron's position is less widely proliferated, less objective. This is why quantum measurements can disturb the system. There aren't enough redundant copies to allow independent observation. Quantum Darwinism thus explains the quantum to classical transition in terms of information theory. Large systems are classical because they proliferate information redundantly. Small systems are quantum because they don't. Why observers agree? So here's the answer to the objectivity problem. Observers agree because they're accessing the same redundant information encoded in the environment. When I look at a chair, photons bounce off the chair into my eyes. When you look, different photons bounce into your eyes, but all these photons carry the same information. Chair at position X, because that's a pointer state, redundantly encoded. So we both see the chair at X, and we agree. In many worlds' language, we both become entangled with the same branch of the universal wave function, the branch where the chair is at X, because that branch has proliferated massively through environmental redundancy. In collapse language, we both observe the same post-collapse state because collapse happens via environmental interaction, which creates redundant information. Either way, quantum Darwinism explains objective reality. Pointer states produce redundant information, and redundancy creates agreement among observers. The emergence of objectivity. Objectivity, in this view, is not a given. It's an emergent property of quantum systems interacting with complex environments. In a universe without environments, a perfectly isolated quantum system, there would be no objectivity. Different observers could become entangled with different aspects of the system's wave function, seeing incompatible realities. But in our universe, Rich with photons, fields, and particles, pointer states proliferate information abundantly. This proliferation creates objectivity, a shared reality accessible to multiple observers. We live in an objective universe not because reality is fundamentally observer-independent, but because the environment mediates between systems and observers, creating redundant information that everyone can access. Classical reality as consensus. Here's a philosophical implication. Classical reality is a consensus reality. It's not that the chair has a position out there, independent of all observers and environment. It's that the chair's interaction with the environment creates a widely accessible description, a consensus, that all observers who interact with that environment will agree upon. This consensus is robust, stable, and objective, but it's not metaphysically fundamental. It's an emergent structure arising from quantum entanglement and information proliferation. In this sense, reality is relational. Objects don't have properties in isolation. They have properties relative to the environment, and those properties become objective when redundantly encoded in that environment. This is a subtle shift from classical metaphysics, where objects simply have properties. In quantum Darwinism, properties are relationships, and objectivity is redundancy. So as you drift deeper, imagine information spreading through space like seeds on the wind. Each photon, each interaction, carries a copy of the world structure, the positions of objects, the states of systems, the arrangement of matter. This information fills the environment, redundant and abundant, creating a shared reality that everyone can access. You see the world not because it exists independently out there, but because you're tuned into the same information broadcast that everyone else receives. And that broadcast, that redundancy, is what makes the world feel solid, real, objective. Now, let us turn to the experiments that confirm decoherence and quantum Darwinism, watching coherence die in controlled laboratory settings. Chapter 6. Experiments, watching coherence die, testing decoherence. For decades, decoherence was a theoretical idea, a plausible explanation for the quantum to classical transition, supported by mathematics, but lacking direct experimental confirmation. But starting in the 1990s, physicists began designing experiments to directly observe decoherence, to watch quantum coherence decay in real time as systems interact with their environments. These experiments are technically challenging. You need to prepare a quantum system in a superposition, control its interaction with the environment, and measure how quickly coherence decays. This requires extraordinary precision, ultra-cold temperatures, and isolation from unwanted environmental noise. But the experiment succeeded, confirming that decoherence happens exactly as predicted by theory. Let's explore some of the most important experiments. Cavity QED experiments. In the 1990s, Serge Haroche and his team at the École Normale Supérieure in Paris performed groundbreaking experiments on decoherence using cavity quantum electrodynamics, cavity QED. They prepared a microwave cavity, a highly reflective box that traps photons. Inside the cavity, they placed a single photon in a superposition of two states, a state with n photons and a state with n+1 photons. Then they sent atoms through the cavity. Each atom interacted with the photon field, becoming entangled with the cavity state. This entanglement caused decoherence of the photon superposition. By varying the number of atoms and measuring the cavity state afterward, Haroche's team watched the superposition decay. The more atoms that passed through, the more decoherence occurred, exactly as theory predicted. Haroche could also control the strength of the interaction, slowing or speeding decoherence. When atoms barely interacted with the cavity, decoherence was slow. When they interacted strongly, decoherence was rapid. This was direct quantitative confirmation that environmental interaction destroys quantum coherence, and that the rate of decoherence depends on the strength of coupling. For this work, Harosh shared the 2012 Nobel Prize in Physics, Ion Trap Experiments. Around the same time, David Wineland at NIST in Boulder performed complementary experiments using trapped ions. Wineland's team trapped single ions in electromagnetic fields, isolating them from their environment as much as possible. They prepared the ions in superpositions of different vibrational states, quantum states of motion. Then they deliberately introduced decoherence by heating the environment or allowing stray electromagnetic fields to interact with the ions. They watched the superposition decay, measuring the coherence time as a function of environmental coupling. Again, the results matched theoretical predictions perfectly. Stronger environmental coupling led to faster decoherence. Weaker coupling extended coherence time. Wineland's work also earned him a share of the 2012 Nobel Prize, highlighting the importance of decoherence research. More recently, experiments with superconducting qubits, used in quantum computers, have provided detailed studies of decoherence. A superconducting qubit is a tiny circuit that can exist in a superposition of two current states. These qubits are exquisitely sensitive to their environment. Stray electromagnetic fields, thermal noise, cosmic rays, all cause decoherence. Researchers at institutions like IBM, Google, and Yale have mapped out the decoherence mechanisms in detail. They've identified the dominant sources of noise, such as two-level systems in materials, magnetic flux noise, and charge noise, and developed techniques to mitigate them. Despite these efforts, decoherence remains the primary challenge in quantum computing. Even at millikelvin temperatures and with extensive shielding, superconducting qubits typically have coherence times of only 10 to 100 microseconds. This is long enough to perform thousands of quantum gate operations, but not long enough for large-scale error-free computation. Overcoming decoherence, either by improving isolation or by using quantum error correction, is the main hurdle to building practical quantum computers, observing the double slit with controlled decoherence. One of the most elegant demonstrations of decoherence involves the double slit experiment with controllable environmental interaction. Researchers at the University of Vienna, led by Anton Zeilinger, performed double slit experiments with large molecules like fullerenes and systematically introduced decoherence by colliding the molecules with gas atoms. At ultra-high vacuum, with minimal collisions, the molecules exhibited clear interference patterns, wave behavior. As they increased the gas pressure, increasing the number of collisions, the interference pattern gradually faded. More collisions meant more decoherence, and eventually the interference disappeared entirely, replaced by a simple double hump pattern characteristic of particles passing through one slit or the other. This experiment directly visualized the quantum to classical transition. At low pressures, the molecules behaved quantum mechanically. At high pressures, they behaved classically, and the transition was smooth, continuous, and perfectly described by decoherence theory. Schrödinger cat states, Chi, some experiments have created and studied Schrödinger cat states, superpositions of macroscopically distinct states, to test the limits of quantum mechanics and decoherence. In 2000, researchers at NIST created a cat state with a single beryllium ion in a superposition of being 80 nanometers apart, a tiny but measurable distance. The superposition lasted only milliseconds before decoherence destroyed it. In 2010, researchers at UC Santa Barbara created a cat state with a mechanical resonator, a tiny vibrating membrane visible to the naked eye, in a superposition of vibrating and not vibrating. This was one of the largest quantum superpositions ever created, but it too decohered within milliseconds. More recently, in 2019, Chinese researchers created a cat state with 18 qubits, representing a superposition of 2 to the 18th equals 262,000 distinct states. Again, decoherence was the limiting factor, constraining how long the state could survive. These experiments push the boundary of quantum mechanics to ever larger systems, but they always encounter decoherence as the ultimate limit. The larger and more complex the superposition, the faster it decoheres. Measuring quantum Darwinism. Quantum Darwinism, the redundancy of information in the environment, has also been tested experimentally. In 2010, researchers at Los Alamos National Laboratory performed an experiment where they prepared a central spin, a quantum bit, in interaction with an environment of surrounding spins. They measured how information about the central spin spread into the environment. They found that pointer states, the states that don't decohere, imprinted their information redundantly into many environmental spins. Non-pointer states, by contrast, left fragmented, non-redundant information. This confirmed Zurek's prediction. Pointer states proliferate information, making it objective and accessible, while non-pointer states do not. More recent experiments with photonic systems have shown similar results, demonstrating that classical information is indeed redundantly encoded in the environment, while quantum information is not. Decoherence-free subspaces. An interesting twist. Physicists have discovered that certain quantum states are immune to specific types of decoherence. These are called decoherence-free subspaces. The idea, if the environment couples equally to certain states, then superpositions of those states don't decohere relative to that environment. For example, if the environment measures total spin but doesn't distinguish between individual qubits, then certain entangled states of multiple qubits can remain coherent even as the environment interacts with them. This is exploited in quantum computing to protect quantum information. By encoding information in decoherence-free subspaces, you can extend coherence times without perfect isolation. Experiments at MIT, Caltech and elsewhere have demonstrated decoherence-free subspaces, showing that clever quantum engineering can partially overcome decoherence. But these techniques work only for specific noise sources. There's no universal decoherence-free subspace. Eventually, some interaction will cause decoherence, the speed of decoherence. All these experiments confirm the same conclusion. Decoherence is real, it's fast, and it scales with system size and environmental coupling exactly as theory predicts. For small systems, single atoms, photons, decoherence can be slowed to seconds or longer by extreme isolation. For intermediate systems, molecules, qubits, decoherence occurs on millisecond to microsecond timescales, even with significant isolation. For large systems, dust grains, macroscopic objects, decoherence is essentially instantaneous, microseconds or faster, far below any observable timescale. The quantum to classical transition is not a mystery. It's a well-understood, experimentally verified consequence of environmental interaction. As you rest, know that the theory is confirmed. Decoherence is not speculation. It's been seen, measured, quantified in laboratories around the world. Quantum coherence is fragile. It dies quickly, irreversibly, when systems interact with their surroundings. And we live in a universe filled with interaction, bathed in radiation, permeated by fields. This is why the world appears classical. Not because quantum mechanics fails, but because it works so thoroughly, so rapidly, that it hides its own strangeness behind the veil of decoherence. Now let us return to Schrödinger's cat and ask, with decoherence in mind, what happens to the poor cat? Chapter 7. Schrödinger's cat revisited the setup. Revisited. Let's return to Schrödinger's famous thought experiment, but now with decoherence as our guide. A cat is in a sealed box with a radioactive atom. If the atom decays, poison is released and the cat dies. If the atom doesn't decay, the cat lives. Quantum mechanics says the atom is in a superposition of decayed and undecayed. This superposition propagates. The poison mechanism enters superposition, then the cat enters superposition. Before you open the box, the cat is, mathematically, in a superposition of alive and dead. But Schrödinger found this absurd, and so do we. Cats are not observed in superposition. The question is, why not? Decoherence enters the box. The answer, the cat is not isolated. Even inside the box, the cat interacts with its environment. The cat is warm, it radiates thermal photons. These photons bounce off the walls, encoding information about the cat's state, alive or dead, into electromagnetic degrees of freedom. The cat breathes, if alive, disturbing air molecules, creating pressure waves, spreading information. The cat's heart beats, if alive, creating vibrations, sound, subtle electromagnetic signals from neural activity. Even if dead, the cat's body has a temperature, a shape, a position, all of which couple to the environment through photon scattering, molecular collisions and gravitational effects. All these interactions entangle the cat's quantum state with the environment inside the box. The superposition of alive and dead becomes entangled with vastly different environmental states, warm body plus breathing plus heartbeat, versus cold body plus no breathing plus no heartbeat. These environmental states are macroscopically distinct. The interference between them is destroyed. Decoherence occurs within microseconds or less, so by the time you open the box, minutes or hours later, the cat's superposition has long since decohered. The cat is effectively either alive or dead, not both, even before you look. Does the cat experience superposition? Here's a subtle question. Does the cat experience superposition before decoherence? In the many worlds interpretation, the answer is no. The cat's consciousness itself is quantum, subject to decoherence. The living cat's brain state is vastly different from the dead cat's brain state, so these branches decohere almost immediately. From the cat's perspective, it experiences either life or death, not both. The superposition exists in the universal wave function, but each branch contains a definite cat experiencing a definite outcome. In collapse interpretations, the superposition collapses due to decoherence, or some related mechanism, and the cat experiences whichever outcome results from the collapse. Either way, the cat never experiences superposition. Decoherence, or the cat's own internal quantum processes, forces a definite outcome long before any external observer opens the box. So the cat is not in some limbo between life and death. It's alive or dead, determined by decoherence dynamics inside the box, independent of external observation. When does collapse happen? This raises an interesting question. When does the collapse, or effective collapse via decoherence, occur? Not when you open the box. That's far too late. Decoherence has already happened. Not when the poison is released, or not released. That's a macroscopic event, also subject to rapid decoherence. The collapse happens at the quantum level, when the radioactive atom decays or doesn't. But even this is entangled with the environment. The atom is never perfectly isolated, so decoherence begins immediately. Within nanoseconds, the atom's state is entangled with photons, electromagnetic field modes, and other environmental degrees of freedom. The superposition of decayed and undecayed propagates into the environment, branching into macroscopically distinct states. By the time the poison mechanism is triggered, or not, decoherence has already transformed the quantum superposition into an effective classical probability. The atom either decayed or it didn't, and the environment knows which. So the cat's fate is sealed almost immediately after the experiment begins, not when you open the box. Observer-dependent reality. Does this mean reality is observer-dependent? That the cat's state changes when you observe it? No. Decoherence explains that the cat's state is determined by environmental interaction, not by your observation. Your observation does entangle you with the cat's state. You become correlated with the branch of the wave function, where the cat is alive or the branch where it's dead. In many worlds, this determines which branch you experience, but both branches exist. In collapse interpretations, the collapse happens via decoherence long before you observe, so your observation merely reveals an outcome that was already determined. Either way, the cat's state is not observer-dependent in any mystical sense. It's determined by physical interaction with the environment. This resolves one of the strangest implications of the Copenhagen interpretation, which seem to suggest that observation by a conscious mind causes collapse. Decoherence shows that collapse, or effective collapse, happens through ordinary physical processes without any special role for consciousness. Why the paradox persists. So why does Schrödinger's cat still puzzle people? Because the language of quantum mechanics is misleading. We say, the atom is in a superposition of decayed and undecayed, and people imagine the atom existing in some ghostly both states at once limbo. But superposition is not a physical state of limbo. It's a mathematical description, the wave function, that encodes probabilities for different outcomes. When decoherence occurs, the wave function doesn't disappear, it's still there, mathematically. But the different branches, decayed versus undecayed, are so thoroughly entangled with different environmental states that interference between them vanishes. So the cat is in a superposition, mathematically, in the universal wave function, but each branch is effectively independent, experiencing a definite outcome. The paradox dissolves when you understand that superposition doesn't mean indeterminacy of experience. It means branching of the wave function, with each branch experiencing a definite outcome. How about bigger cats? Can we scale up Schrödinger's cat? Could we create a superposition of even larger systems? In principle, yes. Quantum mechanics applies to all systems regardless of size. In practice, no. The larger the system, the faster it decoheres, and the harder it is to observe superposition. Creating a superposition of a cat would require isolating the cat from all environmental interaction. No photons, no air molecules, no thermal radiation, nothing. This is impossible with current or foreseeable technology. Even creating superpositions of large molecules, like C60 fullerenes, requires ultra-high vacuum, ultra-low temperature, and extraordinary experimental control. A cat is billions of times larger and more complex, so while Schrödinger's cat is a useful thought experiment, it'll never be a real experiment. Decoherence ensures that macroscopic superpositions are unobservable in practice. The lesson of the cat. What does Schrödinger's cat teach us? That quantum mechanics applies to everything, but decoherence makes large-scale superpositions unobservable. The boundary between quantum and classical is not sharp. It's determined by decoherence timescales. That observation doesn't cause collapse. Environmental interaction does. Consciousness is not needed to explain quantum mechanics. That reality is more subtle than classical intuition suggests. The cat is neither definitely alive nor definitely dead in some absolute sense. It's in a state where environmental interaction has selected a pointer state, alive or dead, making that state objective and definite relative to the environment. The cat is quantum, but the cat appears classical, because decoherence hides the quantum nature behind a veil of environmental entanglement. So as you settle deeper, picture Schrödinger's cat, not as a paradox, but as a metaphor for all of us. We are quantum beings, described by wave functions existing in superpositions, but we're also embedded in environments, constantly interacting, constantly decohering. The definite world we experience, the solid, real, classical world, is not a departure from quantum mechanics. It's quantum mechanics working exactly as it should, sculpting possibility into actuality through the relentless process of decoherence. The cat is alive or dead. You are here or there. Reality is definite, not because quantum mechanics fails, but because it succeeds. Now, let us turn to the future, to quantum computing and the quest to preserve coherence long enough to harness quantum power. Chapter 8. Implications for quantum computing, the quantum computer's promise. Quantum computers promise to revolutionize computation by exploiting quantum superposition and entanglement. A classical bit is either 0 or 1. A quantum bit, a qubit, can be in a superposition of 0 and 1 simultaneously. Multiple qubits can be entangled, creating vast superpositions of many states at once. A quantum computer with n qubits can exist in a superposition of 2 to the power of n states simultaneously. With just 300 qubits, that's more states than there are atoms in the observable universe. This parallelism allows quantum computers to solve certain problems exponentially faster than classical computers, factoring large numbers, simulating quantum systems, optimizing complex functions, searching databases. But there's a catch: decoherence. To perform a quantum computation, you need to maintain quantum coherence throughout the calculation. If decoherence occurs before the calculation finishes, the superposition collapses and you lose the quantum advantage. This is extraordinarily difficult. Qubits are exquisitely sensitive. A stray photon, a fluctuating magnetic field, thermal noise, vibrations, any of these can cause decoherence. Modern superconducting qubits have coherence times of 10 to 100 microseconds. That's long enough for thousands of quantum gate operations, but not long enough for large-scale computations involving millions of gates. Ion trap qubits and other platforms can achieve longer coherence times, seconds in some cases, but they're harder to scale to many qubits. So quantum computing is a race against decoherence. Perform the calculation before coherence is lost. Quantum error correction. One solution is quantum error correction, a technique that uses redundancy to protect quantum information from decoherence. The idea: instead of encoding information in a single qubit, encode it in many qubits using a special code. If decoherence affects one or a few qubits, the redundancy allows you to detect and correct the error without collapsing the entire superposition. This is possible because decoherence affects qubits gradually. It's not an all-or-nothing collapse, but a continuous degradation. By detecting errors early and correcting them, you can maintain coherence indefinitely, in principle. The catch: quantum error correction requires a lot of overhead. To protect one logical qubit, you might need 1,000 physical qubits. So building a useful quantum computer requires millions or billions of physical qubits, a daunting engineering challenge. But progress is being made. Companies like IBM, Google, and IonQ are building quantum computers with hundreds of qubits and demonstrating basic error correction. Within a decade or two, large-scale error-corrected quantum computers may become practical. Decoherence-free subspaces. Another approach: design qubits that are naturally resistant to certain types of decoherence. As mentioned earlier, decoherence-free subspaces are quantum states that don't decohere relative to specific environmental couplings. By encoding information in these subspaces, you can extend coherence times without perfect isolation. Topological qubits, based on exotic states of matter called anyons, are a promising example. These qubits store information non-locally, distributed across many particles, making them intrinsically robust against local decoherence. Microsoft and other companies are pursuing topological quantum computing, though it remains technologically challenging. Quantum supremacy. In 2019, Google announced quantum supremacy, the demonstration that a quantum computer can perform a task that no classical computer can perform in a reasonable time. Google's Sycamore processor with 53 qubits performed a specific calculation in 200 seconds that would take the world's fastest supercomputer 10,000 years, by Google's estimate, disputed by IBM but still impressive. This was a milestone, but the calculation was artificial, chosen specifically to highlight quantum advantage. It wasn't a useful computation. True quantum utility, quantum computers solving real-world problems better than classical computers, remains a goal for the future, and achieving it will require overcoming decoherence. Every advance in quantum computing is, fundamentally, a battle against decoherence. Quantum simulation. One promising application: simulating quantum systems. Classical computers struggle to simulate quantum systems because the number of states grows exponentially with system size. Simulating 300 particles requires tracking more states than there are atoms in the universe, but a quantum computer with 300 qubits can naturally simulate 300 particles, because the quantum computer itself is a quantum system, subject to the same dynamics. This could revolutionize chemistry, materials science, and drug design. Want to know how a complex molecule behaves? Simulate it on a quantum computer. Want to design a new material with specific properties? Use a quantum computer to explore possibilities. Decoherence is still a challenge, but quantum simulation doesn't require as much coherence as other applications, so it may be one of the first practical uses of quantum computers. The fundamental question: how long does coherence need to last? For quantum simulation, maybe milliseconds. For factoring large numbers, breaking encryption, maybe seconds. For large-scale optimization, maybe minutes. Current technology is at microseconds to milliseconds. We're orders of magnitude away from the goal, but progress is steady. Every year, coherence times improve, error correction techniques advance, and qubit counts increase. Within a few decades, we may have quantum computers that can maintain coherence for seconds or longer, long enough to perform transformative computations, and if we succeed, it will be because we've learned to master decoherence, to isolate quantum systems so perfectly that they remain quantum despite the omnipresent environment. There's an irony here. Decoherence is what makes the classical world possible. It's why we can build stable, predictable, macroscopic devices like computers, buildings, and bodies. But decoherence is also the enemy of quantum technology. To build quantum computers, we must undo what the universe naturally does. We must prevent decoherence, isolate systems, preserve superposition. We're fighting against the grain of nature. The universe wants quantum systems to decohere. We want them to stay quantum. This is the technological challenge of the 21st century. Controlling the quantum classical boundary, preserving coherence long enough to harness quantum power, then allowing decoherence to occur in controlled ways to extract useful classical results. It's a delicate dance, holding quantum superposition just long enough, then releasing it at the right moment. Consider the fragility of quantum coherence. It's so delicate, so easily destroyed, that preserving it requires extraordinary effort, ultra-cold temperatures, ultra-high vacuum, isolation from radiation, precise control. Yet this fragility is also what makes the classical world stable. If coherence were easy to maintain, the world would be a chaotic quantum blur. Decoherence is a blessing and a curse. We live in a classical world sculpted by decoherence, but we dream of building quantum machines that defy decoherence, harnessing superposition to compute the impossible. The future may belong to those who master this boundary, who learn to dance between quantum and classical, preserving coherence when needed, allowing decoherence when desired. Now, let us step back and reflect on what all of this means for you, for existence, for the nature of reality. Chapter 9. The Philosophical Implications. What is real? We began with a question. If everything is quantum, why does the world appear classical? The answer, decoherence. Quantum systems entangle with their environment, spread in superpositions into countless degrees of freedom, making interference unobservable. But this raises a deeper question. What, then, is real? Is the wave function real? Or is only the classical decohered world real? Different interpretations of quantum mechanics give different answers. The many worlds view. In the many worlds interpretation, the wave function is the only reality. It never collapses. All branches exist. All possibilities occur, each in a separate world. Decoherence explains why we don't observe superpositions, because we're entangled with one branch. From within that branch, the other branches are inaccessible, but they're still real, still part of the universal wave function. In this view, you exist in countless copies across the multiverse. Every time a quantum event occurs, every particle interaction, every measurement, the universe branches, and versions of you experience each outcome. Most physicists find many worlds conceptually elegant, but hard to accept emotionally. The idea that every possible outcome happens, that countless versions of you are living different lives, feels extravagant. But many worlds takes quantum mechanics seriously, accepting the wave function as real and not adding any extra collapse mechanism. It's the simplest interpretation mathematically, even if it's the most extravagant ontologically. The Copenhagen view. In the Copenhagen interpretation, the wave function is not real, it's a tool for calculating probabilities. Collapse is real, triggered by measurement or decoherence in modern versions. After decoherence, the wave function collapses and only one outcome is real. The other branches never existed. They were just possibilities. This view is more intuitive. There's only one world, the one you experience. But it raises the question, what causes collapse? And why does measurement or decoherence trigger it? Copenhagen doesn't answer these questions. It simply says, this is how nature works. Accept it and move on. Many physicists are pragmatically Copenhagen. They use the formalism without worrying about interpretation, but it leaves the measurement problem unresolved. Objective collapse theories. Some physicists propose that collapse is a real physical process triggered by gravity or complexity. Roger Penrose, for instance, suggests that superpositions of different mass distributions create unstable space-time geometries. When the instability exceeds a certain threshold, the wave function collapses. The GRRW, Girardi-Rimini-Weber model, proposes that wave functions spontaneously collapse at random times, with probability increasing with the number of particles. For single particles, collapse is rare. For macroscopic objects, it's nearly continuous. These theories modify quantum mechanics slightly, adding a collapse mechanism. They predict deviations from standard quantum mechanics at small but potentially measurable levels. Experiments are testing these theories, looking for signatures of objective collapse. So far, standard quantum mechanics without collapse holds up, but the search continues. The relational view, another interpretation, reality is relational. Properties don't exist absolutely. They exist relative to other systems. You experience the cat as alive or dead relative to your interaction with the cat. But another observer, entangled with a different branch, experiences the cat differently. Both experiences are equally real, each relative to the observer. This is close to many worlds, but emphasizes relationality rather than branching. It's inspired by Carlo Rovelli's relational quantum mechanics and quantum Darwinism. In this view, there's no single, absolute reality. Reality is a web of relationships, with each system experiencing the world relative to its interactions. This is philosophically radical, but takes quantum mechanics at face value. Properties emerge from interaction, not from intrinsic existence. Does it matter? Do these interpretations matter? Or are they just philosophy? Untestable metaphysics with no practical consequences? For most purposes, interpretations don't matter. All interpretations make the same predictions for experimental outcomes. They differ only in what they say about unobservable aspects of reality, like other branches in many worlds or the reality of the wave function. But interpretations may matter for quantum gravity, quantum cosmology, or the foundations of consciousness. If we want to understand the universe at the deepest level, we may need to resolve these interpretive questions, and interpretations shape how we think about reality. Many worlds suggest a vast multiverse. Copenhagen suggests a single, collapsing world. Relational quantum mechanics suggest reality is fundamentally relational, not absolute. These are different visions of existence, and they matter for how we understand our place in the cosmos. Decoherence and free will. Does decoherence have implications for free will? In classical determinism, the future is fixed by the past. There's no room for free will, only the illusion of choice. Quantum mechanics introduces genuine randomness. Wave function collapse or branching is probabilistic, not predetermined. But randomness is not freedom. If your choices are determined by quantum coin flips, that's not free will, it's just chance. However, decoherence may provide a middle ground. Your brain is a quantum system constantly decohering. Each moment your quantum state branches, with each branch experiencing a slightly different thought process, influenced by quantum noise in neurons. In many worlds, all branches occur, and versions of you experience each. But from your perspective, entangled with one branch, you experience a definite choice, influenced by quantum indeterminacy, but also by your brain structure, memories, and intentions. Is this free will? It's not classical determinism. It's not pure randomness. It's something in between. A choice influenced by quantum chance but shaped by your history and structure. Whether this counts as free will depends on your definition. but it suggests that the quantum nature of the brain may be relevant to consciousness and decision-making. The emergence of consciousness. Could decoherence be related to consciousness? Some physicists, like Penrose, suggest that consciousness involves quantum processes that resist decoherence, perhaps quantum coherence in microtubules, as in the Ork-Ohr theory, or some other quantum mechanism in the brain. The idea, consciousness might be the subjective experience of wave function collapse or branch selection, occurring in quantum processes within neurons. This is highly speculative. Most neuroscientists believe consciousness emerges from classical neural activity with no need for quantum effects. But it's an open question. The brain operates at body temperature in a wet, noisy environment, conditions hostile to quantum coherence. Yet recent research hints that quantum effects may play a role in photosynthesis, bird navigation, and enzyme catalysis. Could the brain also harness quantum effects? Could decoherence shape conscious experience? We don't know. But it's a fascinating possibility that the quantum classical boundary, the moment of decoherence, might be where subjective experience emerges, living at the boundary. Here's a poetic thought. You live at the boundary. At the quantum level, you're a wave, a superposition of countless possibilities entangled with everything around you. At the classical level, you're definite, localized, solid, real. The boundary between these levels is decoherence. You're perpetually decohering, collapsing from quantum blur into classical clarity moment by moment. And perhaps consciousness is this boundary, the ongoing process of decoherence, the transition from possibility to actuality, the selection of one branch from many. You are the boundary. You're the moment where quantum becomes classical, where potential becomes real, where the universe crystallizes into experience. A final reflection. So as you drift towards sleep, let this vision settle. You are quantum and classical, both. You are a wave, spreading through space, entangled with everything. And you are a particle, localized, definite, here. Decoherence is not the enemy of quantum mechanics. It's the bridge between quantum and classical, the mechanism that creates the world you experience from the quantum substrate beneath. You are living proof of decoherence. Every breath, every thought, every moment of experience is a decoherence event. Quantum possibility collapsing into classical actuality. And that is the nature of existence. Not purely quantum, not purely classical, but both, woven together by the constant, relentless dance of decoherence. Chapter 10. The Boundary of Existence. The question we've answered. We began with a mystery. If everything is quantum, if electrons, atoms, molecules, and even you are fundamentally wave-like, existing in superposition, why does the world appear classical? Why don't we see electrons in two places at once? Why don't chairs interfere with themselves? Why are you here? Definite, solid, not spread across space in a quantum blur. The answer is decoherence, the process by which quantum systems lose their coherence through interaction with the environment. Decoherence doesn't destroy the wave function. It doesn't stop quantum mechanics from applying. It simply hides quantum behavior by entangling the system with countless environmental degrees of freedom, making superpositions unobservable. The classical world emerges from the quantum world through decoherence, and we live in that classical world sculpted by the constant, relentless interaction between quantum systems and their environments. The speed of decoherence. We've seen that decoherence is extraordinarily fast for macroscopic objects. A dust grain decoheres in 10 to the minus 23 seconds. A bacterium decoheres even faster. A human being decoheres essentially instantaneously. Trillions of interactions per second, each one entangling your quantum state with the environment. This is why you never observe yourself in superposition. Not because you're not quantum, but because your quantum nature is hidden beneath the overwhelming speed of decoherence. For small systems, electrons, atoms, carefully isolated molecules, decoherence can be slow. Seconds, even minutes in the best experiments. This allows quantum phenomena to be observed. Interference, entanglement, superposition. But for large systems, decoherence is a wall, an impassable barrier that prevents quantum behavior from manifesting at macroscopic scales. The boundary between quantum and classical is not sharp. It's determined by decoherence timescales. Small and cold systems are quantum, large and warm systems are classical. Everything in between is a gradient, a spectrum, a sliding scale. Pointer states and objective reality decoherence doesn't treat all quantum states equally. It selects certain states, pointer states, that are robust against environmental interaction. For macroscopic objects, position is the pointer basis. Objects appear to have definite positions because position superpositions decohere almost instantaneously, while position eigenstates remain stable. This is why the world looks the way it does, why objects have locations, why we can point to things and say, there, and agree. Quantum Darwinism extends this idea, explaining that pointer states proliferate their information redundantly into the environment, making that information objective, accessible to multiple observers independently. So objective reality is not a given. It's an emergent property of quantum systems interacting with complex environments. The properties we perceive as real are those selected by decoherence and propagated through quantum Darwinism. Schrödinger's cat explained. Schrödinger's cat is no longer a paradox. The cat is quantum, described by a wave function, in superposition, mathematically. But the cat's quantum state decoheres almost immediately, entangling with the environment inside the box. Within microseconds, the cat is effectively either alive or dead, not both, long before any external observer opens the box. Decoherence resolves the paradox by showing that macroscopic superpositions don't persist. They're destroyed by environmental interaction before they can be observed. The cat's fate is sealed by physics, not by your observation. You merely reveal an outcome that was determined or branched by decoherence long before you looked. The challenge of quantum computing. Quantum computing is humanity's attempt to defy decoherence, to preserve quantum coherence long enough to harness superposition for computation. This requires extraordinary effort, ultra-cold temperatures, ultra-high vacuum, isolation from electromagnetic radiation, precise control, and quantum error correction. We're making progress, but decoherence remains the primary obstacle. Every advance in quantum computing is a battle against the universe's tendency to decohere quantum systems. If we succeed, it will mark a turning point. Humanity's mastery of the quantum classical boundary, our ability to preserve coherence at will, to harness the quantum for technology. What is real? The deepest question remains, what is real? Is the wave function real with all its branches existing in a vast multiverse? Or is reality only what survives decoherence, the classical definite world we experience? Different interpretations answer differently. Many worlds says the wave function is all that's real. Copenhagen says only the post-collapse outcome is real. Relational interpretations say reality is what each system experiences relative to its interactions. Decoherence doesn't resolve this question. It remains a matter of interpretation. But decoherence does explain why we see a classical world, regardless of which interpretation is correct. The mystery of quantum mechanics remains. But decoherence pulls back the curtain, revealing the mechanism by which quantum strangeness gives rise to classical familiarity. Living in superposition. You are quantum. This is not metaphor, it's physics. Every electron, every atom, every molecule in your body is described by a wave function existing in superposition. But you're also immersed in an environment, photons, air molecules, electromagnetic fields, gravitational interactions. These entangle with your quantum state, causing decoherence. You decohere billions of times per second, faster than you can perceive, collapsing from quantum possibilities into classical actuality. So you exist in superposition for an instant, then decohere, then superpose again, then decohere, over and over, perpetually. What you experience as continuity, as a stable, solid self, is actually a rapid sequence of quantum states collapsing and reforming through environmental interaction. You are quantum and classical, both, perpetually transitioning between the two, living at the boundary. The beauty of decoherence. There's a strange beauty to this. Decoherence is what makes life possible. Without it, the universe would be a chaotic quantum soup, with no stable structures, no definite properties, no classical world. Decoherence sculpts order from quantum chaos. It selects pointer states, creates objective reality, allows complex structures like stars, planets, and living beings to exist. The classical world is not a failure of quantum mechanics. It's quantum mechanics working exactly as it should, creating stability through interaction, sculpting possibility into actuality through the constant dance of entanglement and decoherence. We live in a quantum universe, but decoherence gives us a classical stage on which to act, to think, to be. The final mystery. One mystery remains unsolved. The measurement problem. Decoherence explains why we don't observe macroscopic superpositions. It explains why the world appears classical. But it doesn't fully explain why we experience definite outcomes, why you see the cat alive or dead, not both, even though the wave function encompasses both. Does the wave function truly collapse? Or do all branches exist with consciousness selecting one? Or is there some deeper mechanism we don't yet understand? This is the final frontier of quantum mechanics, and it may connect to the deepest questions of existence. What is consciousness? What is time? What is the self? Decoherence brings us closer to answers, but the ultimate truth remains just beyond reach, a mystery at the heart of reality, waiting to be unraveled. So as you drift now into sleep, let this journey settle. You've travelled from quantum fields to wave-particle duality to decoherence, 3 pillars of quantum reality. You've seen that the world is quantum at its core but classical in appearance. You've learned that this transition happens through decoherence, the constant interaction between quantum systems and their environments. You've discovered that you are part of this process, a quantum being, perpetually decohering, perpetually collapsing from possibility into presence. And you've glimpsed the mystery at the centre, the unanswered question of what happens when quantum becomes classical, when wave function becomes experience, when the universe observes itself through you. Rest now in this knowledge, now in this knowledge. The quantum world is strange, but it's home. And decoherence is the bridge that lets you walk between the quantum and the classical, experiencing both, belonging to both, living at the boundary where reality is born. And so we return gently from the quantum classical boundary. We've journeyed through decoherence, the mechanism that transforms quantum strangeness into classical familiarity. We've seen that you are quantum fundamentally, but classical in appearance. Not because quantum mechanics fails, but because it works so well that it hides itself beneath the veil of environmental interaction. This completes our foundational trilogy: quantum fields, wave-particle duality, and decoherence, 3 pillars supporting our understanding of reality itself. If this journey has deepened your sense of wonder about the quantum world you inhabit, I invite you to subscribe to Sleep Entangled and continue exploring where science meets contemplation. Like this video to help others discover these mysteries, and share your thoughts below about what fascinates you most about the quantum classical boundary. This is Sleep Entangled, where quantum waves decohere into classical reality, where possibility collapses into presence, and where you, living at the boundary, experience the universe becoming itself. Until we meet again beneath the quantum field, rest easy in the knowing that you are both wave and particle, both quantum and classical, both possibility and actuality, forever dancing at the edge of existence.